Yes, that's good. Thank you very much. So you can now start sharing. And Shrobona is from, I'm not 100% sure where you're located, but I guess at the University of Singapore, because it's the first affiliation, Center for Quantum Technologies. And she will talk about IID and problem-specific random samples of quantum states from quantum Wishart distributions. Curious to hear about that. Shrobona, the stage is yours.
Thank you very much. Thank you very much for giving me the opportunity for presenting my talk in this wonderful event. And so my topic is IID and problem-specific random samples of quantum states from quantum Wishart distributions. So this work has been done in collaboration with Andrii, Lee Wei-jun, Andrew V. Kuhn, and Berthold George Englert. And mostly it was started in Center for Quantum Technologies in National University of Singapore, but we continued, we are still actually continuing and extending this work. And I have been to Tel Aviv University and now at Korea Institute of Science and Technology. But the main part of this work was done in Center for Quantum Technologies in Singapore. And okay, now I start my talk. So plan of the talk is first what I will say what we exactly want to do, and then I'll say about the motivation of this work, the aim of this work, and what do we mean by the problem specificity as stated in the title of the talk. And I will say a little bit about earlier algorithms. So my work is mainly on algorithm, and I will say what were the drawbacks of the earlier algorithm. Then I go to a background and I'll say about the results in a summary. And I'll give an example of a new distribution of random quantum states that we have derived. And I will say about the performance of our algorithm for 1, 2, and 3 qubits. And I will show a comparison of the time taken for our algorithm. And I'll end with conclusions and future directions. So what is the motivation? So what we want to do, we want to generate a problem-specific random sample of quantum states. And this is because random samples of quantum states are valuable in quantum information science. For example, in the numerical testing of the typicality of entanglement in bipart quantum states, or the computation of the average of some quantity of interest over a subset of quantum states, or integration over a region of states, optimization of function on a complicated quantum state space structure, and understanding of the efficiency of a gate implementation or a noise protection scheme. So we have in quantum information science a lot of applications of these random quantum states. So this is the motivation for our work. And as a result, what we want to do, we want to generate random samples of problem-specific distribution. So we just don't want to have a random sample of quantum states for any arbitrary distribution, but on a distribution that is specified by an experimental problem. And we want to generate these random samples in a very small and practical amount of time. We want to generate random samples where the samples are independently and identically distributed. So this ensures that the quality of random samples is good. We want to have some flexibility of the algorithm. We want to have some amount of scale invariance in the algorithm for about at 3 qubits at least. And the algorithm should be simple and easy to implement. What we mean by problem specificity. So for our case, quantum states constitute one of the most studied aspects, for example, in quantum state estimation and quantum tomography. So our problem is specific to this task of quantum state estimation and quantum tomography. So various tools have been developed to unravel the features of quantum states via different kind of measurements and detectors in experimental setups. And statistical tools such as the method of maximum likelihood estimators are used to better understand the data obtained from such devices. And combination of different detected clicks create a specific probability distribution of the quantum state, with the peak being given by the maximum likelihood estimator. And therefore, our task is to simulate the probability distribution pertaining to the setup of measurement and detected clicks with the peak at the maximum likelihood estimator. So this is what we mean by our problem specificity. And these are the exact problems that we want to focus on. So what about the earlier algorithms? So they're an algorithm based on the acceptance rejection method. It's is low. It's very time consuming, and it is unsuitable for high dimensions due to the curse of dimensionality. Then there is something based on the Markov chain Monte Carlo. It is also consuming, but it has another drawback that it generates correlations between the sample points. It is also unstable in high dimensions. Then there is the Hamiltonian Monte Carlo, which is also time consuming, and in the same way it generates correlations between the sample points, and also it's unstable in high dimensions. So we keep in mind all these drawbacks of the earlier algorithms, and we want to circumvent all these drawbacks in our new algorithm. So let us see what is the experimental setup that we consider. So first of all, in experiment, we have these measurements and we have the measurement settings. So what is the theory behind that? The quantum state is denoted by this density operator rho, and qubits, we have two orthonormal basis vectors, and these measurement operators are denoted by pi k for the kth outcome. And according to quantum theory, the probability of obtaining the kth outcome, pk, is given by trace of pi k into rho. In a given measurement setting corresponding to n different outcomes, there are n different probability terms, pk, where k goes from 1 to n. And therefore, for unknown quantum state, if we have d1, d2 until dn number of detected clicks, the probability of obtaining the state is given by this likelihood estimator, which is given by L of rho given d, and it is p1 to the power d1, p2 to the power d2, and until pn to the power dn. And the maximum likelihood estimator is given by the maximum of this likelihood function over the whole probability space. So I now go to my results, a summary of my results. So at first, we find a new distribution of random quantum states according to what we call the non-central Wishart distribution in quantum state space for all finite dimension. We develop an algorithm that circumvents the earlier issues posed by the earlier algorithms that I mentioned earlier. Our algorithm consumes very small amount of time. Our algorithm is general to simulate any target distribution which is well behaved and has a peak in the probability space. Our algorithm is stable, and also it has enough parameters to adapt to many different kind of target distribution that we want to simulate. So the new distribution, I go to my results now, and I'll start with the new kind of distribution on the random quantum states that we have obtained. So suppose this rho is given by this operator form A dagger by trace of A dagger, where A is any rectangular matrix. So it can have different number of columns and still keep the dimension of rows the same. And elements of A are chosen randomly from a Gaussian distribution with, in general, a non-zero mean and a non-identical covariance matrix. So this way of choosing the elements of A generates a row, which again, all such rows form a distribution as random quantum states in the quantum state space. So, and this way of also choosing the elements of A is called the choosing from a Wishart distribution. And the density of the probability density of the density matrices that we obtained as a result of way of choosing this way is called the quantum Wishart distribution. I mean, which we introduce it as a quantum Wishart distribution. And so on the right hand side, there is an example of how this distribution looks. So this is a cross section of quantum Wishart distribution in the 3D block sphere picture. And we show here how the parameters of A determine the nature of this distribution. For example, if we increase the number of columns of A, the height of the distribution increases as shown in this picture. And if we pick a non-zero mean for the elements of A from Gaussian distribution, then the peak of this quantum Wishart distribution is shifted away from the origin. And this has been shown in the figure in the right-hand side in two different ways, in two different quantum Wishart distributions. So now what is the new distribution is obtained. This is just, I'll just say the nature of this distribution. I'll not go to the derivation how we derived, but this we just derived by taking the expectation value of the delta function as shown in the slide, and we get a distribution which is dependent on the determinant of rho and the mean matrix of the Gaussian distribution, covariance matrix of the Gaussian distribution, dimension of the density matrix rho, and the number of columns n, capital N, of the matrix A. And this gives us a lot of handle so that this distribution can be made flexible to meet our requirements of the algorithm. To keep it flexible, we can tweak those different parameters in our own way to suit our need to obtain a certain kind of distribution that we would like. And it can have peak inside the quantum state space, or also it can have a peak exactly on the boundary of the quantum state space. So this gives us a lot of freedom in choosing these distributions. So I'll go to an example, one qubit, what we call the TRINE measurement setting. So on the left, we have what we call a target distribution. That is a distribution which is obtained from the experimental data. And so we have three outcomes. And this probabilities are given as functions of R and phi, where R and phi are the block parameters. And the detected number of detected clicks we just choose is to be arbitrary, where 7, 10, and 13. It can be anything, any number, and still we would be able to implement our algorithm. So it has that amount of flexibility. And we have a maximum likelihood function dependent on this detected clicks. And to match this target distribution obtained from the experimental data, we want to have a proposal distribution. And to match the profile of the target distribution on the left, we choose a suitable number of columns of the matrix A and choose a suitable mean matrix, the value of the mean of the Gaussian distribution, so that we match it exactly as the target distribution on the left. So I'll just show it visually how it is done. So sampling for the TRINE measurement setting. So suppose in the left hand side, this darker blue colored distribution is the target distribution that we want to match. And we have on the right hand side, on the right, the lighter blue color distribution, which is our proposal distribution, where we have already chosen the height of the proposal distribution, which is close to the target distribution. But you see the peak is not exactly the same, but we have actually already chosen the value of the mean such that the distance of the peak from the origin is same for the proposal and the target. So what we do, so we want to match the peak, so we just rotate it, and you just see where we rotate, the target and the proposal just almost coincide, and we cannot recognize one from the other. So after that, we do the acceptance rejection sampling, and we obtain the sample points, which is according to the target distribution. So this is pretty, so the thing that has helped us is that we can choose the number of columns of A according to our wish, and also the value of the mean that would help us match the proposal distribution with the target distribution in this way. So this is an example of the acceptance rate that we obtain from our algorithm. And you see, if we use uniform distribution with acceptance rejection, which is given by this green line, the acceptance rate is 0.05, which is very low. And actually, if we increase the height of the target distribution, this gets even much lower, and there is no flexibility of the algorithm with respect to the uniform distribution. But using the Wishart distribution, which you see by the red and the blue graphs, it is over 0.4, which is 40%, over 40%, and this is a very good acceptance rate using acceptance rejection algorithm. And unlike the uniform distribution, if we use this quantum Wishart distribution, then we can maintain this acceptance rate at over like 40%. Even the worst case scenario is even like for target distribution, which is very highly peaked, we can just adjust our proposal distribution to match the target distribution, still keep it at as high as 40%. So this is an example, and we now go to the higher number of qubits, matching how to match the peak. We employ a different method because rotation does not give physical points in 2-qubit space. There we have to develop an alternate method to match the peak position of the proposal distribution to match the target distribution. And suppose the peak of the target distribution is rho p, and then we apply the calculus of variations to solve for this peak as follows. We just have this equation. It is pretty simple to solve. And we get a covariance matrix of the Gaussian distribution, underlying Gaussian distribution, which is dependent on the value of n, capital N, which is the number of columns, the value of D, the dimension of the density matrix, and the mean matrix M, and the peak density matrix rho p. And we can choose this M according to our own choice and fix the peak of the distribution. So we can have a little more simplifications to this. So we can fix this M2 equal to 0, and then we have the following covariant matrix. And it is dependent on this rho p, n, and d, and that's it. So we have this covariance matrix. We sample according to the quantum Wishart distribution according to the covariance matrix, and it will have the peak exactly at the same position as that of the target distribution, and the capital N will also determine the height we want to match. So we have the flexibility to match the target distribution. And this is much simpler to handle. So I want to go to the results for 2 qubits. So we have double tetrahedral measurement settings. This is an example. And we have 16 probability operators, and they are given by pi k is equal to pi L cross pi L1 for first party and pi M2 for second party. And for measurement data, do you want D22 until D16, the likelihood function and the target distribution has the form of pi, product of k going from 1 to 16 and trace of pi k rho to the power dk. And if we use uniform distribution for sampling, the acceptance rates decrease exponentially with increasing number of detected clicks, with an acceptance rate of about 10 to the power minus 8% for detected clicks reaching 100. And if we use Wishart distribution, the acceptance rate remain as 1%, even if the detected clicks reach 100 with appropriate proposal distribution. Likewise, we go to 3 qubits and we have the triple tetrahedral measurement settings. And we have 64 probability operators here. And the measurement operators are given by pi k go to pi L1 cross pi M2 cross pi M3. And for measurement data D1, D2 until D64, the likelihood function is the likelihood function is given by this product of trace of pi k rho to the power dk until for k 1 to 64. And if we use uniform distribution for sampling, the acceptance rates decrease exponentially with increasing number of detected clicks, with acceptance rate of less than 10 to the power 9% for detected clicks reaching dk 10. This render is completely impractical. But if we use Wishart distributions, the acceptance rates remain as 10 to the power minus 5, even if the detected clicks reach dk to the power dk is equal to 10 with appropriate proposal distribution, and which allows one to obtain a sample of 10 to the power 5 within 100 hours, which is actually a very practical time frame. And so time taken for various algorithms, I'll just give a comparison, which is I give the comparison using only tetrahedral measurement settings. So this is an example. For 1 qubit, we have this for using uniform distribution, we have 8 hours. For using Hamiltonian Monte Carlo, it's 16 hours. Moreover, it has correlations between the sample points. And for Markov chain Monte Carlo, we have 16 hours, which also has, this method also creates correlations between the sample points. And using uniform plus Wishart distribution, it's only 5 minutes. For 2 qubits, we cannot obtain any reasonable amount of random sample using uniform distribution, Hamiltonian Monte Carlo, or Markov chain Monte Carlo in any practical amount of time. And it only takes 31 hours, which is 1 day and a half, almost like even less than that. And for 3 qubits, it's the same using uniform distribution, Hamiltonian Monte Carlo and Markov chain Monte Carlo. There is absolutely no practical way to obtain any reasonable amount of random samples, whereas we can do it a million points using Wishart uniform Wishart distribution. I think 10 to the power 5 points using Wishart distribution is by only 100 hours. So, and also the quality of these random samples are very good because they are completely independent and identically distributed with no correlations among them.
So, Shrobona, yeah, I just wanted to mention we should come to the conclusions, but there you are.
Yeah, okay. Okay, so I will come to my conclusions. Is we produce truly independent and identically distributed sample points from the space of quantum states, and we do this in a very short amount of time. Our algorithms are very stable. We have enough parameters to adapt to different kind of target distribution in the quantum state space. And our algorithm is flexible without any compromise on the quality of the random sample generated. The quality of random samples are of high quality for all different kind of distributions in the quantum state space. However, there is one drawback, and we are kind of improving on this. And there is also some paper which has improved on this already. So this algorithm is not suitable for dimension higher than that of 3 qubits because of the curse of dimensionality. So what can be the future direction to explore the possibilities of the non-central Wishart distribution in sampling algorithms in more details, which you are currently doing now? to extend the sampling algorithms in higher dimensions, employing a different sampling algorithm other than acceptance rejection method, and to find applications of the non-central Wishart distribution in quantum channel capacities, like it has found applications in classical multiple input and multiple output channel capacities. So with that, I end my talk. Thank you very much for your kind attention and listening to my talk. And I'm happy to answer any questions regarding this. Thank you.
Thank you, Shrobona, for this nice presentation. So yeah, we have a bit of time for some questions in case there is some. Don't see any in the chat. Maybe in Discord there was something.
Yeah, no questions in the Discord. Yeah,
no question Discord. So I might have I don't know if it's a stupid or complicated question. So maybe since this is not my field, do not know a lot about. So what makes your approach? Why is that so more? Is there an intuitive understanding why your approach is so much more? It seems like it's much more powerful, right? In terms of the time that you compare, and others don't even work for 2 or 3 qubits. So what is? Can you give an maybe for me as a non-expert?
Yes. For example, in the earlier approaches, one of the using acceptance, so there can be some methods like the Monte Carlo methods or the acceptance rejection method. So without the Wishart distribution, the main thing that we use the Wishart distribution. This gives it the power that it has, because first of all, it automatically generates density matrices. But in the earlier Monte Carlo algorithms, there was a problem because it first generated a matrix and then it saw whether it's a density matrix using the positivity condition, using the determinant, and that took a lot of time. So checking the positivity took a lot of time in the other algorithms. However, in our case, the positivity is automatically generated like within a fraction of a second. So this saves a lot of time than the Monte Carlo methods. And also it has the flexibility because it is problem specific, because it actually mimics this Wishart distribution, mimics the shape of this likelihood function. So it is easy to match the proposal with the target distribution in this way. And it gives us a lot of flexibility so we can match it very quickly. So the main point of difference is that we use the Wishart distribution, which is very closely related to the likelihood function, and also the positivity condition is generated very automatically in a fraction of seconds. So that gives the main advantage.
Okay, cool. Thanks. Yeah, that helped. That helped. Okay, good. So I think there is no. There's one question maybe, or maybe just a comment. I'm impressed with the speaker goes to tackle her one mean matrix, which I imagine grows. Okay, I think it's just a comment. So I don't really understand it. I don't know if you want to comment on that.
Okay, and I actually didn't follow the comment though.
Yeah, I think it's okay. There was no really question involved. So I think if there's nothing else, so thanks Shrobona again for this nice presentation.
Thank you very much for giving me the opportunity.